Okay, friends, good morning to all of you. Last time we have completed state machines, now starts process and threads. So, in this chapter, we will study active objects, processes, and threads, modeling multiple flow of control, modeling inter-process communication, building thread safe abstractions. Not only is the real world a harsh and unforgiving place, but it is a very busy place. Events may happen and things may take place all at the same time. Therefore, when you model a system of real world, you must take into account its process view, which encompasses the threads and processes that form the system's concurrency and synchronization mechanisms. In the UML, you model each independent flow of control as an active object that represents a process or a thread that can initiate control activity. A process is a heavyweight flow that can execute concurrently with other processes. A process is a heavyweight flow that can execute concurrently with other processes. A thread is a lightweight flow that executes concurrently with other threads within the same process. Where process is heavyweight, flow can execute concurrently with other processes, but thread is a lightweight flow that execute concurrently with other threads within the same process. So in the UML, each independent flow of control is modeled as an active object. An active object is a process or a thread can initiate control activity. As for every kind of object, an active object is an instance of class. Active object is an instance of class. In this case, active object is instance of an active class. Active object is instance of an active class. Also, as for every kind of object, active objects can communicate with one another by passing messages. Although here message passing must be extended with certain concurrency of semantics to help you to synchronize the interactions among the independent flows. So the UML provides a graphical representation. This figure shows the active class. Active class name is this in this example active class name is blackboard controller. It have attribute as current knowledge source. It have operations, it have signals. First is attribute, second operation, third signals. So active class are kinds of classes. Active classes are kinds of classes, so have all the usual compartment for the class name, attributes, and operations. Active classes often receive signals which you typically enumerate in an extra compartment. So, what are the terms and concepts of process and threads? An active object is an object that owns a process or thread. Active object, it is an object that owns a process or thread and can initiate control activity. An active class is a class whose instances are active. A process is heavyweight flow that can execute concurrently with other processes. And thread is a lightweight flow that can execute concurrently. within other threads with the same process. Graphically, an active class is rendered as a rectangle. Graphically, active class is rendered, that means shown, as rectangle with thick lines. Processes and threads are shown as stereotyped active classes. So, flow of control in a purely sequential diagram, there is one flow of control, that is the one thing and one thing only can take place at a time. When a sequential diagram starts, control is routed at the beginning of the program and operations are dispatched one after another. Even if there are concurrent things happening among the actors outside the system, a sequential program will process only one event at a time. Sequential program will process only one event at a time, queuing or discarding the concurrent external events. This is why it is called a flow of control. If you trace the execution of sequential program, you will see the locus of execution flow from one statement to another in sequential order. You might see actions that branch, loop, or jump about, and if there is any recursion or iteration, you see the flow circle back on itself. Nonetheless, in the sequential system, there would be a single flow of execution. So, in a concurrent system, there is more than one flow of control. More than one thing can take place. In sequential, it is only one at a time, but in concurrent flow, more than one control flow at same time at same place. In a concurrent system, there are multiple simultaneous flows of control, each rooted at the head of independent process or thread. If you take a snapshot of concurrent system while it's running, you will logically see the multiple loci of execution. So in UML, you see active class represents a process or thread. That is the root of independent flow of control, and that is concurrent with all peer flow of control. You can achieve true concurrency in one of three ways. First, by distributing active objects across multiple nodes. Second, by placing active objects on nodes with multiple processors. And third, by combination of both methods. So what concept is classes and events? Active classes are just classes, albeit ones with a very special property. Active classes represents an independent flow of control, whereas plain classes embodies no such flow. In contrast to active classes, plain classes are implicitly called passive because they cannot independently initiate control activity. You can use active classes to model common families of processes or thread. In technical term, this means that the active object and instance of active class reflects a process or thread. So by modeling concurrent objects with active objects, by modeling concurrent system with active objects, you give a name to each independent flow of control. When an active object is created, The associated flow of control is started when active object is destroyed. The associated flow of control is terminated. Whenever the active objects or associate active objects are alive, then flow of control there is flow of control. If they are destroyed, then the flow of control associated with is terminated. So active classes share the same properties as all other classes. Active classes may have instances, active classes may have attributes and operations. Active classes may participate in dependency, generalization, and association relationships. So active classes may use any of the UML's extensibility mechanisms, including stereotypes, tagged values, and constraints. Active classes may be realization of interfaces. Active classes may be realized by collaborations at the and the behavior of active class may be specialized by using state machines. So you can model the collaboration of active and passive object, the terminations of the diagrams. Active object may appear at the target of event in the state machine. Speaking of state machines, both passive and active objects may send and receive signal events and call events. So what are standard elements? So a state process is heavy light, which means that it is thing known to the operating system itself and runs in an independent address space. Under most operating systems such as Windows and Linux, each program runs as a process in its own address space. In general, all processes on a node are peers of one another, contending for all the same resources accessible on the node. Processes are never nested outside one another. If the node has multiple processors, if the node has multiple processors, then true concurrency on that node is possible. If the node has only one processor, there is only one illusion of true concurrency carried out by underlying operating system. A thread is lightweight. It may be known as operating system itself. More often, it is hidden inside the heavier weight processes. It runs inside the address space of the enclosing process. All the threads that live in the context of process are peers of one another, contending for the same resources accessible inside the processes. Threads are never nested inside one another. Threads are never nested inside one another. In general, there is only the illusion of true concurrency among threads because it is a process, not threads. They are scheduled by nodes operating system. So what is the communication happens between two objects, two process or two threads? So when objects collaborate with one another, they interact, passing messages from one to other. In a system with both active and passive objects, there are four possible combinations of interactions that you must consider. First, a message may be passed from one passive object to another, assuming there is only one flow of control passing through these objects at a time. Such an interaction is nothing more than the simple invocation of an operation. Second, a message may be passed from one active object to another. A message may be passed from one active object to another when that happens, you have interprocess communication, and there are two possible styles of communications. First, one active object might synchronously call all operations of other. That kind of communication has rendered semantics. That means the caller calls the operation, caller waits for receive the accept of call, the operation is invoked, return object is passed back to the caller, and then to continue on the independent path. For the duration of call, the two flows of control are in the lockstep. Second, one active object might asynchronously send a signal or call an operation of another object. That kind of communication has a mailbox semantics, which means the caller sends signals or calls the operation, then continue on its independent way. In the meantime, the receiver accepts the signal or call whenever it is ready and continue on its way after it is done. This is called mailbox because two objects are not synchronized, rather than one object drop offs the message for other. For example, in first case, you can call one one object can call another object directly. They communicate with each other, and in second, one object can send a mail to other objects. Whenever other object is free, then the other object can see the message received from the first object. Then third, the UML, third, message passed from active object to passive object. So a difficulty arises if more than one active object at a time passes flow of control through one object, through one passive object. So that is, in that situation you have to model synchronization of these two flows very carefully. So see in this figure, this is three active objects. This is backboard is active objects, then knowledge source is also active objects, then blackboard controller is also active objects. So in UML, you render a synchronous message full arrow, that is synchronously message can be sent, and asynchronously this is full arrow. This full arrow indicates a message, synchronous message can be sent. This half arrow known as asynchronous message, and it have a control flow of control, message 1, message 2, message 3, that is flow of sequence. So then fourth, a message may be passed from passive object to active object. At first glance, it may seem illegal, but you remember that every flow of control is rooted in some active object. You will understand the passive object passing a message to active object has same semantics as an active object passing message to an active object. Then synchronization, visual for a moment, the multiple flows of control that wave through a concurrent system. When a flow passes through an operation, you say that at a given moment, the locus of control is in the operation. If that operation is defined for some class, you can also say that a given moment the locus of control is in a specific instance of that class. You can have multiple flows of control in one operation, and you can have different flows of control in different operations. You can have multiple flows of control in one operation, and you can have different flows of control in different operations. So what is process views? Active object plays an important role in visualizing, specifying, constructing and documenting a system's process view. A process of view is system encompass the threads and processes that form systems concurrency and synchronization mechanisms. This view primarily addresses the performance, scalability, and the throughput, that is output of the system. With the UML, the static and dynamic aspects of these views are captured in the same kind of diagram as for the design, that is the class diagram, interaction diagram, activity diagram, and state chart diagrams, but with the focus of an active classes that represent these threads and processes. So, what are the common modeling techniques? Modeling multiple flows of control. Building a system that encompasses multiple flows of control is hard. Not only do you have to decide how the best divide work across concurrent active objects, but once you have done it, you also have to devise the right mechanisms for communication and synchronization among your system's active and passive objects to ensure that they behave properly in the presence of these multiple flows. For that reason, it helps to visualize the way these flows interact with one another. You can do that in the UML by applying class diagram and interaction diagram containing active classes and objects. So to model multiple flows of control, identify the opportunities for concurrent actions and reify each flow as active class, generalize common sets of active objects into an active class. Be careful not to over engineer the process view for the system by introducing too much concurrency. Consider a balanced distribution of responsibilities among these active classes. Then examine the other active and passive classes with which each collaborates statistically. Ensure that each active class is both tightly cohesive and loosely coupled relative to these neighboring classes, and that each has the right set of attributes, operations, and signals. Capture these static decisions in class diagrams, explicitly highlighting each active class. Consider how each group of class collaborates with one another dynamically. Capture those decisions in the interaction diagrams. Explicitly show active objects as the root of such flow. Identify each related sequence by identifying it with the name of the active objects. Pay close attention to communicate among the objects. Pay close attention to communication among the active objects. Apply synchronous and asynchronous messaging as appropriate. Pay close attention to synchronization among these active objects and passive objects which they collaborate. Apply sequential, guarded, or concurrent operations semantics as appropriate. So, modeling interprocess communication, that is modeling of an IPC. As a part of incorporating multiple flows of control in your system, you also have to consider the mechanisms by which objects that live in separate flows communicate with one another. Across threads, objects may communicate via signal or calls, the latter of which may exhibit either synchronous or asynchronous semantics. Across processes, you usually have used two different mechanisms. The problems of interprocess communication is the problem of interprocess communication is computed by the fact that is distributed system process may live on the separate nodes. Classically, there are two approaches to the IPC: message passing and remote procedure calls. In UML, still model these asynchronous or synchronous events respectively. But because there is no longer simple interprocess calls, you need to add on your signals with further information. So to model interfaces, so model the flow of control, consider which of these active objects represent processes and which represent threads. Distinguish them using appropriate stereotype. Model messaging using asynchronous communication. Model remote procedure calls using synchronous communication. Informally specify underlying mechanisms for communication by using nodes, or more formally by using collaborations. So, what we studied in this chapter, that is hints and tips. A well-structured active class and active objects represent an independent flow of control that maximizes the potential for true concurrency in the system. It is not a fine-grained that it requires a multitude of other active elements that might result in an over-engineered and fungal process architecture. Carefully message communicate among peer active elements, selecting between asynchronous and synchronous messages. Carefully treats each object has a critical region, using suitable synchronous properties to preserve of semantics in the presence of multiple flows of control. Explicitly distinguishes between process and threads semantics. So when you draw active class or active object in UML, show only those attributes, operations and signals that are important in understanding in the abstraction in the context. Explicitly show all operations synchronization properties. So next part is time and space. Up till now we have completed interaction, use case diagrams, interaction diagrams, activity diagrams, event signals, state machines, process and threads. Now time and space regarding the UML. So in this chapter we will study time duration and location, modeling time constraints, modeling the distribution of objects, modeling objects that migrate, dealing with real time and distributed system. The real world is harsh and unforgiving place. Even may happen at unpredictable times and demand a specific response at specific time. A system's resources may have to be distributed around the world. Some of those resources might be even move about rising issues of latency, synchronization, security, and quality of service. Modeling time and space is an essential element of an of any real time and or distributed system. You use a number of the UML's features, including timing marks, making expressions, constraints, and tagged values to visualize, specify, construct, and document these systems. Dealing with real-time system and distributed system is hard. Good models reveal the necessary and sufficient properties of systems, time and space characteristics. So when you start to model most software systems, you can usually assume a frictionless environment. Messages are sent in zero time. Networks never go down. Workstations never fail. The load across your network is always evenly balanced. Unfortunately, the real world does not work in this way. That is, the way messages do take time to deliver. Sometimes never get delivered. Network goes down. Workstation do fail. Networks load. In these situations happens in the real world. But your assumptions that your messages seen in zero time, networks never go down, workstation never fail, the load across network are always evenly balanced, but it does not happens in the real world. So therefore, when you encounter systems you must operate in the real world, you have to take account the issues of time and space. A real-time system is one in which a certain behavior must be carried out at a precise, absolute, or a relative time and within a predictable, often constrained duration. At one extreme, such systems may be hard real-time and require complete and repeatable behavior within nanoseconds or milliseconds. At other extreme, models may be never real time and also require predictable behavior but on the order of seconds or longer. A distributed system is one in which components may be physically distributed across nodes. These nodes may represent different processes physically located in the same box. They may be even present computers that are located half a world away from the other. So to represent modeling needs real-time distributed system. UML provides graphical representing timing expressions, timing constraints, and locations as shown in this figure. So there are three objects: client, map server, and map cache. So for client, location is console, map server is location is server, and map cache is location is mission server. So they can communicate with each other. This is a, this b, a colon then some message. This is known as a timing mark. So what is a timing mark? A dot execution time is less than 10 millisecond. See the figure carefully. The next, what are the terms and concepts regarding time and space? A timing mark is denotation for the time at which an event occurs. Graphically, a timing mark is formed an expression name given to the message. A time expression is an expression that evaluates an absolute or relative value of time. A timing constraint is a semantic statement about the relative or absolute value of time. Graphically, a timing constraint is rendered as for any constraint that is a string enclosed by brackets and generally connected to an element by dependency relationship. Location is the placement of the components on node. Graphically, location is rendered as tagged value, that is a string enclosed by brackets and placed below the element's name or as a nesting of components inside the nodes. So, what is a time? Real time systems are, by their very name, time critical systems. Events may happen at regular or irregular times. In response to event must happen at predictable absolute times or at predictable times relative to the event itself. The passing of message represents the dynamic aspects of system. So when you model the time critical nature of a system with the UML, you can give the name to each message in an interaction to be used as a timing mark. Messages in an interaction are usually not given names. Then location. Distributed system by their nature encompasses components that are physically scattered among those nodes of the system. For many systems, components are fixed place at the time they are located on the system. In other systems, components may migrate from node to node. In UML, the model deployment view of the system by using deployment diagrams that represent the topology of the processors and devices on which your system executes. Components such as executable libraries, tables reside these nodes. Each instance of node will own instances of certain components and each instances of an component will be owned by exactly one instance of node. See in this figure, location, this is nesting location, log.exe, this is vision. This part shows the location. Location is equal to, second part, location is equal to router. So what are the common methods of modeling the time critical nature of a system? Common method, the absolute time the relative time between the events. Modeling the absolute time of an event, modeling the relative time between events, and modeling the time it takes to carry out an action are the three primary time critical properties of real time systems for which you will use timing constraints. To model timing constraints for each event in an interaction, consider whether it must start at some absolute time. Model that real-time property as a timing constraint on the message. For each interesting sequence of messages and interaction, consider whether there is an associated maximum relative time for a sequence. Model that a real-time property as a timing constraint on the sequence. For each time critical operation in each class, consider its time complexity. Model those semantics as timing constraints on the operation. So modeling the distribution of objects. When you model the topology of a distributed system, you will want to consider the physical placement of both components and class instances. If you locus if you focus the configuration management of deployed system, modeling the distribution of components is especially important in order to visualize, specify, construct, and document the placement of physical things such as executables, libraries, and tables. If your focus is functionality, scalability, and output, that is throughput of the system, modeling the distribution objects what is improvement. Deciding how to distribute the objects in a system is big problem, and not just because the problem of distribution interact with the problem of concurrency. Naive solutions tend to yield profoundly poor performance, and over-engineering solutions are not much better. In fact, they are probably worse because they usually end up being brittle. So to model the distribution of objects for each interesting class of objects in your system, consider its locality of reference. In other words, consider all its neighbors and their locations. A tightly coupled locality will have neighboring objects close by. A loosely coupled one will have distant objects. Tentatively allocate objects closest to the actors that manipulate them. Next, consider patterns of interaction among the related sets of objects. Co-locate sets of objects that have high degrees of interactions to reduce the cost of communication. Partitions sets of an objects that have low degrees of interaction. Next, consider the distribution of responsibilities across the system. Redistribute your objects to balance the load of each node. Consider also issues of security, validity, and quality of service, and redistribute your objects as appropriate. Render this allocation in one of two ways: by nesting objects in nodes of deployment diagram, by explicitly indicating the location of objects as tagged values. So to model the migration of objects, select an underlying mechanism for physically transporting objects across nodes. Render the allocation of an object to a node by explicitly indicating its location as a tagged value. Using the become and copy stereotyped messages, render the allocation of object to a new node. Consider the issues of synchronization, that is keeping the state of cloned object consistent, and identity, that is preserving the name of object at it moves. So what are the hints and tips regarding time and space. A well structured model with the time and space properties expose only those time and space properties that are necessary and sufficient to capture desired behavior of the system. Centralize the use of those properties that so that they are easy to find and easy to modify. When you draw a time or space property in UML, give your timing marks meaningful names. Clearly distinguish between relative and absolute time expressions. Show space properties primarily by tagged values. Use the nested form only when it's important to visualize the placement of elements across deployed system. So last part from this chapter is state chart diagram. So in this chapter we will study modeling reactive objects, forward and reverse engineering. The state chart diagram is one of the most important out of five diagrams in UML modeling the dynamic aspects of system. A state chart diagram shows state machines. An activity diagram is a special case of state chart diagram in which all or most of state are activity states and all or most of the transitions are triggered by completion of activities in the source states. Thus, both activity and state chart diagrams are useful in modeling the lifetime of an object. However, whereas an activity diagram shows the flow of control from activity to activity, a state chart diagram shows the flow of control from state to state. You use state chart diagram to model dynamic aspects of system. For the most of part, this involves modeling the behavior of reactive objects. A reactive object is one whose behavior is most characterized by its response to events dispatched from the outside its context. A reactive object has a clear lifetime whose current behavior is affected by its past. State chart diagrams may be attached to classes, use cases, or entire systems in order to visualize, specify, construct, and document by the dynamics of the individual objects. State chart diagrams are not only important for modeling the dynamic aspects of the system but also for constructing executable systems through the forward and reverse engineering. So, what is a state chart diagram? Consider the investor whose finances the building of new high rise. He or she is unlikely to be interested in the details of building process, the selection of materials, scheduling of trades, and many meetings about engineering details that are actives are important. Activities are important to the builders, but far less so that a person is bankrolling the project. The investor is interested in getting a good return on the investment, and that also means protecting the investment against risk. A really trusting investor will give the builder a pile of the money, walk away for a while, and return only when the builder is ready to hand over the keys to the building. Such an investor is really interested in the final state of the building. So in UML, the model event ordered behavior and object using state chart diagram. This is the example of state chart diagram. In this ideal connected processing, cleanup, transmitting. These are the different states. So initially, the state is ideal. It goes to the receiving. Then in receiving is biggest state. In this, there are nested different states. So whenever it receives at receiving, it is initial of receiving, that is connected, then processing, then cleanup, then sent to the ideal. So then transforming, then after transforming to s- send facts to the ideal. See the figure carefully. So what are the terms and concepts regarding state chart diagram? A state chart diagram shows a state machine emphasizing the flow of control from state to state. A state machine is behavior of that specifies the sequence of states an object goes through the during its lifetime in response to events. Together with it responses to those events, a state is a condition or situation in the life of an object during which it satisfies some conditions, performs some activity, or waits for some event. An event is a specification of significant occurrence that has a location in time and space. In the context of state machines, an event is an occurrence that stimulates can trigger a state transition. A transition is a relationship between two states indicates the object is a first state will perform certain action and enter the second state when specified event occurs and specified conditions are satisfied. An activity is going non-atomic execution within a state machine. An action is an executable atomic computation that results in a change in the state model to the return of an value. Graphically, a state chart diagram is a collection of vertices and arcs. So a state chart diagram is just a special kind of diagram and shares a same common properties as do all other diagrams, that is a name and graphical contents that are projections into the model. So what are the contents? So state chart diagrams commonly contain simple states and composite states. Transitions including events and actions. A state chart diagram is basically projection of an element found in state machine. That is, the state chart diagrams may contains branches, force, joins, s- action states, activity states, objects, initial states, final states, history states, and so on. These are the some examples from activity diagrams. In activity diagrams, we have seen the initial state, final state, fork, join, branch, etc. We have seen. So indeed, state chart diagrams may contains any and all features of the state machines. So what distinguishes activity diagrams from state chart diagram is that activity diagram is based on projection of elements found in activity graph, a special case of state machine in which all or most states are activity states and which all or most transitions are triggered by completion of activities in the source state. So what are the common use? You use state chart diagrams to model the dynamic aspects of system. These dynamic aspects may involve this event ordered behavior of any kind of object in any view of system architectures, including classes, active classes, interfaces, components, and nodes. When you see state chart diagram to model some dynamic aspects of system, you do so in the context of virtually any modeling element. Typically, however, you will use state chart diagrams in the context of systems as a whole or subsystem or a class. You can also attach state chart diagram to use cases. You when you model dynamic aspects of system, a class or use case, you will typically use state chart diagrams in one way. So to model reactive objects, a reactive or event driven object is one whose behavior is best characterized by the response of events dispatched from the outside of the context. A reactive object is typically ideal until it receives an event. When it receives an event, its response usually depends on previous event. After object responds to an event, it becomes ideal again, waiting for next event. For this kind of object, you will focus the stable states of an object to event that trigger a transition from state to state and action that occurs on each state change. In contrast, you will use activity diagrams to model a workflow or to model an operation. Activity diagrams are better suited to modeling the flow of activities over time, such as you would represent in a flow chart. So, what are the common modeling techniques? Most common purpose for which you will use state chart diagrams in model the behavior of reactive objects, especially instances of classes, use cases, and the system as a whole, whereas the interaction model and behavior of the society of objects working together. A state chart diagram models the behavior of single object over the lifetime. The activity diagram models the flow of control from activity to activity, whereas the state chart diagram models the flow of control from event to event. When you model the behavior of reactive objects, you especially specify three things: stable states which objects may live, the events that trigger the transition from state to state, and actions that occur on each state change. Modeling the behavior of reactive object also involves modeling the lifetime of object, starting at the time of object's creations and continuing until its destruction, highlighting the stable state in which the object may be found. So stable states represents a condition in which object may exist for some identifiable period of time. When an event occurs, the object may transition from state to state. These events may also trigger self and internal transitions in which the source and target of transitions are the same state. In reaction to an event or state change, the object may respond by dispatching an action. When you model the behavior of reactive objects, you can specify its action by trying it to a transition or state change. In technical terms, a state machine whose actions are all attached to the transitions is called as merely machine, and a state machine whose actions are attached to the states called mover machine. Mathematically, the two styles have equivalent power. In practice, you will typically develop state chart diagram to use combination of merely and more machines. So to model a reactive object, select the context of state machine, whether it is a class, a use case, or a system as a whole. Select as its initial and final state for the object. To guide the rest of your model, possibly state the pre and post conditions of initial and final states respectively. Decide on the stable states of an object by considering the conditions in which the object may exist for some identifiable periods of time. Start with high level states of an object and only then consider its possible substates. Decides on meaningful partial ordering of stable states over the lifetime of the object. Decide on the event that may trigger a transition from state to state. Model these events as triggers to transitions that move from one legal ordering of states to another. Attach actions to these transitions and or these states. Consider the ways to simplify your machine by using substates, branches, poles, joins, and history states. Check that all states are reachable under some combination of events. Check that no state is dead end from which no combination of events will transition the object out of that state. Trace through the state machines either manually or by using tools to check against expected sequences, events, and their responses. So, what are hints and tips regarding state chart diagrams? When you create state chart diagram in UML, remember that every state chart diagram is just projection on the same model of the system's dynamic aspects. A single state chart diagram can capture the semantics of single reactive objects, but no one state diagram can capture the semantics of entire non-retrieval system. A well-structured state chart diagram is focused on communicating one aspect of the system's dynamics. A well-structured state chart diagram contains only those elements that are essential for understanding that aspects. A well-structured state chart diagram provides details consistent with its level of abstraction. A well-structured state chart diagram uses balances between styles of merely and more machines. When you draw state chart diagram, give it a name that communicate its purpose. Start with modeling the suitable states of objects, then follow with modeling legal transition from state to state. Address branching, concurrency, and object flows as a secondary consideration, possibly in separate diagrams. Layout its elements, minimize that cross. So here we have completed fifth chapter. Next lecture we will start sixth chapter. If you have any query regarding this chapter, you can ask. Otherwise, write your roll numbers. Otherwise, write your roll numbers in chat box and log out. आज तारीख कितनी है?